in Argentina, who's going to be talking about actions of algebraic quantum groups.
Thank you very much. Thank you, the organizers, for inviting me. Okay, well, this talk is based on joint work with Eugenia Ellis and Ana Gonzalez. They are both from Uruguay, Universidad de la. And I will start by outlining our motivation for studying algebraic quantum groups. And then before introducing algebraic quantum groups along their actions and coactions, I will reveal the definition of a Hopf algebra. And then, yes, conclude with the problem we studied and the results that we've got so far. I'm afraid.
It's not working.
Okay. So let's start with the group case. So let G be a, this, for me, groups are always discrete. So let G be a group, A an algebra, and H a subgroup. I will write P for the projection to the coclasses. And what is a left action of the group G on the algebra? Well, it's a homomorphism from the group to the automorphism group of the algebra. And I will write a left action like that, okay? G acting on the element A. And then for any left H algebra now A has an action of the subgroup H. The induced left G algebra is defined as follows, and this is a work of Guillermo Cortiñas and Eugenia Ellis. And this induced algebra is, the objects are functions from the group to the algebra with some conditions on the support. The function is the support of the function, that is the elements of the group, where the function is non-zero. And if we project the support and then we count the cardinality, it's finite. And it also satisfies this condition related to the action of the subgroup H to the elements of the algebra. And this algebra has a left action of G, of the group G, given by that. Okay, so that is the in algebra. And this construction has very nice properties. It defines a functor actually from the category of H algebras to the category of G algebras, and satisfies, for example, that if our algebra A was already a G algebra, then we recover the original algebra up to isomorphism. If we start with a trivial subgroup of G, then this int algebra is just functions of finitely supported from G to A. If our algebra is the complex numbers with trivial action, we recover finitely supported functions to the complex numbers. I would determine the coclasses. And these are the properties that we are interested in. So this int algebra has a structure, has a left G action. So we can take this cross product with G. And this algebra is isomorphic to a matrix algebra. These are matrices with coefficients in the cross product of A by H, because A has a left action by H. They are matrices with only finitely many non-zero entries, and they are indexed by the coclasses. So this isomorphism in particular tells us that this cross product algebra, this int algebra cross G and H cross H are Morita equivalent. In particular, they have the same K theory. And if you have heard about algebraic KK theory, if not, it doesn't matter. It's like an algebraic version for Kasparov's KK theory. And we have this relation. These are abelian groups. This is an isomorphism of abelian groups. So this tells us that this int functor is a left adjoint to the restriction function. Okay, but we are going to be interested in this property of the int algebra.
Like a Frobenius restriction. It's like a Frobenius.
Something like that. Yeah. So if we consider the algebra of all functions from G to A, and we equip this algebra with this left H action, we can think of the int algebra as a subalgebra of this. It's a subalgebra of the invariance for this action, okay? Because we need some condition of the support, but this is a subalgebra of invariance for this action. That is the int algebra. So we were interested in what can we extend this construction of int algebra to algebras that have an action of, no, I don't know, another structure, anything that is not a group. And the first observation is that if we have an action of the group G on A, this action extends to an action of the group algebra on A. And the group algebra is a Hopf algebra. So the action of G on A extends naturally and makes the algebra A into a modular algebra over Hopf algebra. So our first attempt was to think about, well, can we extend this construction to Hopf algebras? So let me recall what is Hopf algebra. So what is Hopf algebra? Start with the unital 8 algebra, with the unital complex algebra 8, and we say that it is a Hopf algebra if it is equipped with a co-multiplication, a co-unit, and an antipode. What is a co-multiplication? Well, it is an algebra homomorphism from the algebra to the tensor product. And this property is the co-associativity. So let me take a minute to explain what is the co-multiplication. If maybe I can write here or there. Same. Okay. So what is the multiplication on an algebra? The algebra is called 8. So if we have a co-multiplication, a multiplication, we have a linear map from the tensor product to the algebra, okay? A co-multiplication is a map that goes the other way. And what this multiplication is associative. What does it mean? Well, it means that we have a commutative diagram that is an associative multiplication. Okay, we can multiply the first two factors and then take the identity. We arrive to this product, or we can apply the identity to the first factor and then multiply. We arrive to the tensor product. And this goes to 8 by multiplying. So the multiplication is associative if this diagram commutes. Okay, so this co-associativity means, okay, now you inverse for arrows. You apply the co-multiplication. And then here we can co-multiply for tensor identity or identity tensor co-multiplication. And this outer diagram commutes. This is the condition of the co-associativity, okay? And the same with the co-unit and the antipode. A unit of an algebra, what is? It's the morphism from the complex numbers to the algebra. Well, the co-unit is a homomorphism from the algebra to the complex numbers. And this property is like reversing all arrows in the property of a unit. And note that we are using Sweeter notation for the co-multiplication, okay? If we apply delta to an element 8, that is an element in the tensor product, so it is a linear, a finite sum of elementary tensors. And we will write this finite sum as H1 tensor H2. So this means, okay, you first apply the co-multiplication to 8, and then you apply co-unit tensor identity or identity tensor co-unit, and we'll cover that. And Hopf algebras also have an antipode, which is a bijective algebra anti-homomorphism. This means that it reverses the product, and that satisfies this condition. This condition can be seen as that the antipode is like an inverse for the identity, but not for the decomposition, but for the convolution product. Okay. So if we have any group G, any discrete group G, the group algebra is a Hopf algebra with this structure. This is the co-multiplication, this is the co-unit, and this is the antipode. Now, if H is a finite dimensional Hopf algebra, we can consider its dual, that is, or linear functionals from H to the complex numbers, and it is also a Hopf algebra with the product given by the convolution, that is like the transpose of the co-multiplication, and the co-multiplication given like by the transpose of the multiplication. With this is the co-unit, that is, we apply F to the unit element of the algebra. And the interesting part is that if we take duals twice, we will cover the original Hopf algebra up to isomorphism, okay? But this only works in the finite dimension. So if we have a group, if you have a group G, the group algebra is always a Hopf algebra. But if we take the dual, we can identify this dual with all functions from the group to the complex numbers. And this is not a Hopf algebra anymore with the structure that I explained above. And what is the problem? The problem is the commultiplication, because if we think of the commultiplication as the transpose of the multiplication, it takes values on the dual of the tensor product, which makes strictly contains the tensor product of the duals. So we cannot define a commultiplication. Okay, so what about actions of the Hopf algebra? Okay, so H is a Hopf algebra and A is a unital algebra. We say that A is a left H module algebra. If it is a left H module, it has an action on the left of the Hopf algebra. The action also respects the product of the algebra A, meaning this. Here again, we're using Sweeter notation for the multiplication, okay? And the element H must act like an identity on the identity of the algebra. But we also have this co-unit of H. So if we start having an algebra A with an action of a group D, is the same as having this algebra with the structure of a module algebra over this Hopf algebra. Okay. And moreover, for finite dimensional Hopf algebras, actions of the algebra correspond to coactions of its dual. We know that this dual is again a Hopf algebra, and we have this relation between actions and coactions. So what is a comodular algebra? Okay, we reverse the arrows in the definition of an action. So say that A is a right H comodular algebra. If we have a linear map rho from A to A tensor H, we also have a Sweeter notation for coactions. And if you look carefully, these conditions is that reverse the arrows in the definition of an action. So, as I mentioned before, this is the property that for finite dimensional Hopf algebras, for example, you can find it in the book of Susan Montgomery. And it says that if H is a finite dimensional Hopf algebra, then A being a left H module algebra is the same as being a right H dual comodule algebra. So what happens in our case of groups? Okay, so suppose our group is finite. So the dual is again a Hopf algebra, and the dual is all functions from the group to the complex numbers. And suppose we are given, let's say, we go from actions to coactions. So given a left module algebra A over the group algebra, this would be the notation for the action. We can define a coaction of the dual. So this is the dual. And so what does it do rho on an element A? Well, we take the sum over all elements over all G in the group, which is finite, and we act with G in A and tensor with this is the characteristic function of the element G, which is an element here. And now if we start with the coaction of the dual, how do we recover an action of the Hopf algebra? Okay, so now suppose we are given a right comodule algebra A over function, complex functions on G, and this will be the notation for the coaction, again, Schnittler notation. So this is an element of A, this is an element of functions over G, and we can define an action of the group algebra on A by this. An element D acting on A will be, okay, evaluate this function on G and multiply by A0, that is an element of the algebra. Okay, so but if our group is not finite, which is the adequate notion of a dual for this group algebra, we would like to have a dual like lands in the same category, okay, as with what happened with finite dimensional Hopf algebras. And here they appear the algebraic quantum groups. This is the adequate framework for our work. So the point is that we consider the group algebra as an algebraic quantum group. And if we take the dual as an algebraic quantum group, we'll recover finitely supported functions on G, which is contained in the dual that I mentioned before. And this dual is again an algebraic quantum group. And for algebraic quantum groups, we have the same duality results that we have for finite dimensional Hopf algebras. That is, if we take dual twice, we recover the original algebraic quantum group up to isomorphism. And moreover, if A is a left G-module algebra, or A is a left G-module algebra, if and only if A is a right co-module algebra over the dual, okay? So it's like the same theory that for finite dimensional of algebras. So what is an algebraic quantum group? Yes.
So which definition are you taking for quantum group?
I'm going to give you the definition now.
Ah,
So an algebraic quantum group is a regular multiplier of algebra with non-trivial invariant functionals. So now I will explain what is for me a regular multiplier of algebra and what does it mean for invariant functions. Okay. So we start with a complex algebra with non-degenerate product. That means that condition above. And we consider the multiplier algebra of G. What is the multiplier algebra? It's the largest unitary algebra that contains G as an essential two-sided ideal. We can construct this multiplier algebra thinking of left and right multipliers, okay? But for us, it is enough to know that it's the largest unitary algebra that contains G as an essential two-sided ideal. G already has a unit, then it coincides with G. So we say that G is a regular multiplier of algebra if there exists a non-degenerate homomorphism delta, that is a commultiplication, but now this delta takes values in the multiplier algebra of the tensor product. Okay, for finite dimensional Hopf algebras, the commultiplication was a map from H to H tensor H. Now we allow this commultiplication to take values in the multiplier algebra of the tensor product. The first condition is some technical condition that is needed to define some maps. And we also ask for co-associativity, the same that this diagram here, okay? But what happens now? Here I wrote, this is the identity of G tensor delta. This map is a map from G tensor G. So we have to extend this map to the multiplier algebra, okay? That is why we ask the commultiplication to be a non-degenerate homomorphism. This allows to extend this tensor of maps to the multiplier algebra. Here again, this means we extend this map to the multiplier algebra, and this diagram commutes. Okay, so we have a commultiplication with the notion of co-associativity. We have linear homomorphisms, the co-unit. This is the co-unit, this is the condition for the co-unit. Note that here, again, I'm using Sweeter notation, but we have to be very careful in this case because the commultiplication takes values in the multiplier algebra. So, for example, delta of X may not be an elementary tensor, may not be a finite sum of elementary tensors, okay? So there is a notion of Sweeter notation, but we have to be careful with that. And we also ask for a bijective anti-homomorphism, which is the antipole. Okay, so what happens with Hopf algebras? Every Hopf algebra is a multiplier of algebra. So this is like the generalization, the generalized notion for Hopf algebras if we start with a non-unitary algebra, okay? Okay, so now a multiplier of algebra G is an algebraic quantum group if there exists a non-zero linear functional phi from G to the complex numbers that verifies this condition. And this equality is in the multiplier algebra of G, that one that is here is the unit of the multiplier algebra. In Sweeter notation means that x1 phi of x2 equals phi of x times 1. And this phi is called a left invariant functional, which is unique up to scalar. It may not exist, okay? If I have a multiplier of algebra, it may not have invariant functionals. And this is like the algebraic notion of the Haar measure for locally compact groups. Now, if we have a left invariant functional, we can construct a right invariant functional by recomposing with the antipode. A right invariant functional satisfies now this condition. We will say that an algebraic quantum group is compact if it is unitary, and we say that an algebraic quantum group is discrete if it has an integral, which is an integral is an element T that for any other x in G, we have this condition, okay? This is an integral. So a compact algebraic quantum group is a Hopf algebra with invariant functionals, okay? And if G is a finite dimensional algebraic quantum group, that is the same of G being a finite dimensional Hopf algebras. That is, finite dimensional Hopf algebras, we know that they are multiplier algebras and they have invariant functionals. And if we have a finite dimensional algebraic quantum group, then it has a unit, which is a Hopf algebra. Okay, and what about the dual? How we construct the dual? So we have G, an algebraic quantum group. Then for every element x in G, we can define this functional. We take the invariant functional phi, and we define phi sub x like that. Phi sub x on an element y is just phi evaluated on y times x. And we consider all the functionals, and we write like that. This lives in the dual of all functions, okay? So now if we take the product and the coproduct of G, and we use this idea of transpose the product to obtain a coproduct and to transpose the coproduct to obtain a product, with this structure, G dual becomes an algebraic quantum group. And what about the invariant functional? Okay, so every element in the dual by construction is of the form phi sub x for some x in G. So we will define the invariant functional. This will be a right invariant functional, and it defines as follows. Eta on this omega will be just evaluate the co-multiplication on the element x. That defines your function of the. So we have again an algebraic quantum group. And we have this theorem. This is a paper of Alphonse Van Dale from 1998. It says that if G is an algebraic quantum group, then we take duals twice and we recover again the original algebraic quantum group up to isomorphism. So the same as for finite dimensional Hopf algebras. Okay, so let's return to our example of groups. Let G be a group, and we consider all finitely supported functions from G to the complex numbers. So we can write each function f as a finite sum, a linear combination of characteristic functions of elements of the group. And this is a discrete quantum group with this structure. Well, the multiplication is just pointwise, and the co-multiplication, that delta, lies in the multiplier algebra of the tensor product. That is, all functions defined on G times G. And we define the co-multiplication like this. So it is enough to define it on the characteristic functions. So delta on the characteristic function of an element G is the sum over all elements in the group of these tensors. Okay, so this is not an element in the tensor product, but is an element of the multiplier algebra of the tensor product, because our group G might not be finite. And there we have the co-unit. The co-unit on the characteristic function is the delta Kronecker, that is 1 if G equals the neutral element and 0 if not. The antipode takes the characteristic of the inverse. The invariant functional is always 1 in every characteristic function. And moreover, I said it was a discrete algebraic quantum group, so I need to show you an integral, and the characteristic function of the neutral element is integral in this case. And if we take the dual as an algebraic quantum group, we recover the group algebra, okay? And the group algebra is compact as an algebraic quantum group because it is always unital. And this works in general. If we start with the compact algebraic quantum group, that is, it has unit, then the dual is discrete, that is, it has an integral. So we have the same notion as for finite abelian groups when we take duals. So now we know what is an algebraic quantum group. Okay, but what about actions and coactions? So now let D be an algebraic quantum group and A complex algebra. We will say that A is a left D module algebra. If it is unital as a left D module, that is, we have a left action of D, unital means this condition that every element of A can be written as a finite sum of elements of G acting on A, and an element X must respect the product. That's the same thing as for Hopf algebras, okay? Again, we are using Sweeter notation for the computation. And the same for comodule algebra. So A is a right G comodule algebra if there exists an injective homomorphism. Now, this homomorphism takes values in the multiplier algebra of the tensor product, not just tensor product, okay? That verifies those conditions. So we have actions, we have coactions, and we have this result, again, that relates actions of the algebraic quantum group with coactions of the dual. So if G is an algebraic quantum group and A is a complex algebra, then A is a left D module algebra if and only if A is a right D dual comodule algebra, and we can interchange left, right, both sides. So for example, let's consider G, the algebraic quantum group, which has an invariant function of 5. G is a right G comodule algebra with the coaction given just by the co-multiplication. Okay, so delta on an element Y, we use the usual Sweeter notation that I mentioned, A1 tensor Y1 tensor Y2. And if we consider this coaction, the dual action of G hat is given like this. So if we want to act with a dual, we know that the elements of the dual are this form. Phi is the invariant functional. And this element acting on the left of Y is, okay, take Y sub 1 here and evaluate phi on Y sub 2 times X. It's like, okay, you apply the co-multiplication to this element and then you apply identity tensor phi. So what was the original problem? Recall that I started talking about the group and action of an algebra. So we have a group G, a subgroup H, and a left H algebra A. And we can construct a left G algebra in HG of A. And the property that this G algebra has, one of the properties is that these algebraic cross products are Morita equivalent. Okay? This was the case for groups. So first, we have a notion of cross product for algebraic quantum groups. It's the same notion of smash product for Hopf algebras. Okay, so if we have a left G module algebra, the smash product A smash G is just the tensor product, and we use the action of D to twist the multiplication. So this is the way that we multiply the elements of the smash product. Okay, so this is our problem. Suppose we have an algebraic quantum group G. We have some quantum subgroup U, a good enough quantum subgroup U. We have A, but it is a left U hat module algebra, and we want to construct a module algebra A tilde, which is a module algebra over G dual, such that these smash products become Morita equivalent. Can we do that? Can we construct this A tilde? Well, we hope so. But our first problem was to identify the good quantum subgroups. So what is a quantum subgroup for us? For example, there is a notion of closed quantum subgroups for locally compact groups, locally compact algebraic, locally compact quantum groups, yes. And there is also a notion of quantum subgroups for Hopf algebras, but we didn't find the notion for this precise framework. So let me define what is for us a compact quantum subgroup. We start with D, an algebraic quantum group. So a compact quantum subgroup will be, this U is a compact unimodular algebraic quantum group. So it's compact, so it's unital. Here, unimodular means that left invariant functionals and right invariant functionals coincide. And we also need a surjective homomorphism pi from D to U. So these will be our compact quantum subgroups. For example, these are the two cases that we wanted to study. If our algebraic quantum groups is finitely supported functions in the group D, we can consider as a compact quantum subgroup functions over H, where H is any finite subgroup of D. And this P is just the restriction function. And if D is a finite algebraic quantum group, that is a finite dimensional Hopf algebra, U is a semi-simple finite Hopf algebra with a surjective homomorphism from G. So these cases, we're going to study those cases now. So the original problem was, okay, if we have any algebraic quantum group with a quantum subgroup, can we construct this A tilde? So we focus on these cases. What do we do? Well, in both cases, we consider a module algebra, a left module algebra over the dual of U. As U is finite dimensional, then it's just all the functionals. So we start with this A and we proceed as follows. First, we take the tensor product of A with G, the algebraic quantum group, and we know this tensor product with the right structure of an U hat module algebra. We define an action on the right in this tensor product, which is a module algebra action. Okay, then we take the invariant for this action. So our A tilde is just the elements of the tensor that are invariant under the action of the elements of U hat. This invariant means this, okay? We always have this counter there. So we take the subalgebra of invariance. Then we endow this subalgebra of invariance with the structure of the left G hat module algebra. And then we show that if we take the smash products, these algebras are Morita equivalent, okay? So we have a partial answer to our original problem for these cases. So these are the results that I mentioned for the case of groups and for the case of finite algebraic quantum groups. So in the case of groups, we start with a group D, H a finite subgroup, and A left module algebra with units over the group algebra of H, which is the dual of the original. This is like the U hat, okay? So as I mentioned, I take the tensor product of D with A, that is all finitely supported functions from D to A. We do that with the right action of the group algebra of H and take the algebra of invariance. So in this case, we have finitely supported functions from D to A. To A, yes, we take the subalgebra of invariance and we do this algebra with the left module algebra over the group algebra of G. And we prove that we have this Morita equivalence. And for the case of finite dimensional algebraic quantum groups, recall that the finite dimensional algebraic quantum group is just a Hopf algebra, finite dimensional Hopf algebra. So we take H, the finite algebraic quantum group, U, the compact subgroup, and A module algebra with units over U hat, over the dual. And we do the same procedure. We take the tensor product of A with H, define a right module algebra action of U hat, that tensor product. We take the invariant, the algebra of invariance, and we endow this algebra of invariance with a left action of H hat. then we can take these smash products and we prove that these smash algebras are Morita equivalent. So this is our result, and we are working on, okay, can we generalize this construction to any algebraic quantum proof? And the first step is to define a right action of U hat over the tensor product. That's the first problem that we have. We are still working. Okay, so these are the references that appears in the talk.
Questions?
Maybe a nice question. Can you return to the previous slide?
I don't know.
Let's see if the technology allows.
I think.
For example, in the C-star algebra world,
Yes, there's a notion of.
okay. For example, we have this algebra of compact support. In this case, we can complete with certain topology and obtain a C-star algebra, the reduced C-star algebra of the group with condition in A. And my question is, if you know, if, for example, if you take the completion of all these constructions, recover the construction in the C-star algebra world?
I don't think so. We find, you know, Stephen Biles has a construction for these things, and he worked with von Neumann algebras because they have this condition that the double commutant recovers the original, and he uses that, and we cannot recover that in this case. So I don't know if it's the same, it's just complete.
More questions? Alex?
So for instance, for some groups, usually the group algebra has more structure, like quasi-triangular algebra, given algebra. So in the case that you have that structure, can you say something for this two answer?
I don't know. Haven't thought about it. Haven't thought about it. It's really easy to work with groups and the group algebra because it's easy to define actions and coactions because of the complexification. But no, we didn't think about the structure of the group algebra. We cover something interesting on that. No.
Any more questions? So let's coffee outside. So we start again at 10:30, 11:30. ¿Hay café? No, 11:30. Mario. Organización. Sí, bien. Estaba ahí que quería sacar mi charla, pero pues la burocracia no me Sí, no, pero es que esta lista hace rato. Pero por ejemplo, digo, si lo hago, nunca lo hago. Quiero como salir de no, pero yo ya por eso. No, es que no funcionó el Zoom.
Sí, si es más también es problema.
Es que sí,
no le da
porque
siempre más también.
A través de Zoom,
Bueno, yo me encargo después de
la pones en Zoom, que no la graban y la pones en Zoom. Pero no, si aparentemente hay gente en YouTube. Sí, en vivo. Pero como que no llegaron con el, como eso lo maneja alguien, no sé, como ni siquiera de ciencia, no, pero sí, alguna administración, pero como horrible. Entonces como que esa gente no apareció por ahí, pues no se podía comentar. Pero lo otro chistoso es que el teclado está raro. Entonces tú vas adelante y no siempre va adelante, a veces va atrás. Sí, es muy raro. Macho. Y no hay manera de que nos dé un jugador que no haya dado clases. Ya está. Bueno. ¿Qué más echas? Que se demora un tiempito. También es que no te da la paciencia. En algún punto ahora aparece. No, pero ya ahora va a aparecer.
Al final, mira,
Lo que pasa es que antes eran
aporte y contribuciones previsionales.
Sabía que sí.
pero ahora con trabajo. Ahora como bueno, déjame ver.
A uno les entiendo.
Sí, no, pero igual molesta un poco.
Algo más aparte de eso.
Pero molesta menos.
Eso sí,
¿Cómo le llamas? 5. Después de 2 no va 1. Pero si se va adelante, ahora sí va 1. Ya te
Ah, no.
y también, miren, es que si se va adelante y después se para, va atrás.
Ah, muchas gracias.
Pero después sí va atrás. Okay. Pero de 2 a 1 no, de 2 tiene que ir adelante. Porque yo no sé qué está haciendo, pero es muy raro. Entonces, no me lo guardo. Yo ver mi curso. Ahora, bien, usted. Ah, pues sí, pues es responsabilidad de
Tira siempre.
Tira
siempre. ¿Quién? ¿Qué vas? ¿Todo bien? Estaba regresando hasta ahora. Más fácil, ¿todo bien? ¿Qué? Sí. No, pero ya regresé en serio. Vaya,
Esa imagen que le está mandando.
ok,
Sí. 11:30.
Normalmente para los organizadores, ¿no?
Gracias.
No conozco muy bien. Por el lado del revista. Todavía no, o sea, sí.
¿Cómo se viene?
No puede ir para nada.
Grados de facultad. Pues sí. Bueno, grados interfacultades. ¿Este?
Profesor, we have empanadas.
¿Qué son los empanadas?
De cuello.
Muy bien, ¿cómo puede pasar?
Y listo, entonces, volvamos esta tarde. Cuando bueno, no, esas son y organizaciones
Posible.
la media hora.
Programas interfacultades. Pero aquí dice microbiología. ¿Ese no es? Posible. Ese poco. ¿De mí? Ese viene. Sí. El piso. Ese. Posible. ¿Error? Este me sale mire, ese me sale de microbiología. ¿Qué es la diferencia? Este boca. Posible. Porque sale, ¿eso tiene que ver o no tiene que ver? Creo que sí, correcto. O sea, este usuario con quién entró. ¿Cómo es su correo?
Voy a enviar un correo para lo pueda.
Ok, MA chaval.
Me lo
MA. Chaval. Aquí dice maestría en ciencias de microbiología, Instituto de Biotecnología. ¿Eso es?
Pues debería ser ese, pero no llega a los correos.
Ok, bueno, asumamos que es ese. Ahí está. Entonces ya se hace correo.
Un momento que creo que seguramente mal contacto. Ahí hay un chat. Yo empecé. Ahí hay un chat que yo empecé. Dije como buenos días. Contestar las manos.
Cámaras. Mira, maestro. Buen encuentro. Ahora, ¿quién está? ¿Puede compartir? Ok. Bien. Hola Julián, buenos días. Martín, el usuario que es UN70 va a ser cohort. Está grabando. Listo, ya es con ya puedes compartir pantalla, ¿sí? Ya es con Vale, entonces se va a compartir pantalla aquí. Selecciona. Ahí, ¿usted me está escuchando ahí, Julián, por el micrófono del salón? Perfecto, voy a colgar la llamada acá.
Hola.
Hola, Julián.
No. Listo, ahí estoy viendo la presentación.
¿Listo? ¿Ya está viendo la presentación?
Sí, señor.
Muchas gracias. Si aparecen dos cosas, el teléfono, ver, o sea, Iván, esto es una llamada esto es como una llamada telefónica con video. Y lo que está haciendo la mesa es marcando la dirección de este salón. Entonces, si pasa eso que aparece, quita la imagen y aparece en el teléfono, hay que volver a marcar. Pero quien nos debe marcar es la mesa de ayuda. Entonces, me avisa y yo le escribo a Julián o le marco a la extensión. Vuélvanos a marcar que se queda la llamada. O sea, si se cae la llamada, ellos tienen que volver a marcar. Porque es que depende. Pues, digamos, yo no puedo solucionarlo. Tienen que solucionarlo. ¿Sí? Ellos que nos marcan. ¿Listo? Entonces, o si usted tiene el teléfono, se cayó la llamada. Marquen otra vez. O mandan un WhatsApp. Bueno. Punto bajo. Uy, ya.
Se le sale el rango, ¿cierto?
No, pero no me devuelve al 1. No sé por qué. Ah, sí, ahora es como raro. Pues quiero volver al 1. Le doy acá. Pasando cuando tendría que retroceder. Bueno, un poco raro. Ah, bueno, yo me mando. Y si no, entonces con la flecha, ¿cierto?
Adelantar y pasar.
No, a las 1:30. Pero este marcador es súper chistoso, tú le haces adelante, haces como para atrás, haces para adelante.
No depende, no depende.
¿Haces que lo presione?
Sobre, ahí literalmente sobre.
Claro, pero vamos. Ah, sí.
No, yo sé lo que no tengo los contactos. Mejor. Pues yo,
No hay otra cosa.
La tercera vez que
Yo tenía un problema, pero a mí no me gusta hacer.
¿Alguna vez he hecho pues hablemos. Sí, 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 pues por una cosa como lógica un poco humanizando ese meterse en el sol dándose por ver yo nunca voy a electricidad. Yo lo que primero conozco pero sí sería bueno después un análisis pero se salario me parece
So now the technology is working, but the speaker has a little problem. So we will be fashionably late as usual. Yeah. 1 or 2 more patients. It will still take like 5 minutes or more, so maybe I mean, we need to use the restroom like this. It's a good moment. Sorry. There's still food outside. There's bad quality coffee. Just don't run away. Keep close to the area.
Pero es que está ahí con el banco. Pero no es que te voy a decir a ti, porque después la gente no sabe. Pues sí. No, que tuvo algún problema en eso. La primera charla tuvimos los datos de tecnología de este sitio humano. ¿Desde qué charla? No, sí.
¿Sí? ¿Yo puedo? Ah, bueno. Hay alguien raro que está pasando.
¿Pero los llamaron al banco? Ah, no, pero si los llamaron, no. Yo no sé. Es raro. Sí, los llamados están. Pero no me
Hay un correo que llegó al ¿Qué pasó? No, porque
Pues tiene ahí un problema con el banco, no sé qué. Pues vamos a ver si logra solucionar y si no cancelamos.
O hablo yo.
No, pero no se puede porque la gente, digamos, hay gente que no está acá que quiere entrar a la sala. No,
Hablo yo.
Yo
siempre estoy presto para hablar. Me llaman a hablar. Acá tengo un par de tablet. Pero raro, ¿sabes?
Alguien tiene ¿ah?
Yo nunca me lo
Alex, para que podemos mirar la sesión y usted la presenta.
Ah, vale.
Bueno,
Y ya no tengo.
El doctorado es que
como en la época del servicio que el país no le gustaba el speaker. Siéntese y pase y habla contigo.
Pero igual, como él decía que todos eran bobos, ya terminaba hablando de eso. No es que era pero la gente
Vinimos, vamos de la verdad. Hay un puesto ahí.
No, porque cuando si es una cosa si no rápido, claro, en 5 minutos le va a hacer la cuenta.
no, claro. Y además tiempo que se lo devuelven.
Hackearon un importante
Yo antes no lo hice, pero ahora lo hago. Es lo que dos toca ir adelante para ir atrás.
No hay pago, no es que no hay pago,
Porque ahora va atrás. Entonces, para ir atrás, lo primero va adelante y después la última lo que hizo.
no mandar usarlo y mandar apoyar información sensible y comunicarse directamente con él. Porque pasa que se esconde como una basura. Precisar información. Manda mucho basura. Sí.
una herencia. Que necesitaba alguien que la recibiera.
Pero refiero a los que su investigación de mucho valor, entonces por eso ya publicados en revistas. Para que le suba la moral. No, ya sé, están haciendo cosas importantes.
Ya, cuando usted diga, estoy haciendo tan nervioso, que estoy empezando
Hay un punto ahí.
a la voz.
Me toca tomar decisiones como organizador. Lo que es usar es más breve. Casi ven ya 3 por la mañana. Sería por la tarde, pero por la tarde ya no. La tarde igual ya está ocupada también por los subsidios. Que tengo que. Yo por ejemplo por la tarde.
De camino.
Canta que es un pedo. No sigas dando
Ay, no, después dijeron.
Pedrito ahí, teoría.
La experiencia por la música. Por ahí.
Se va a hacer.
Oh, ok.
Bueno, pero todo bien.
Sí, sí,
Eso es importante.
Okay.
Sorry for the delay. Life happens. Okay. So it's a pleasure to introduce Mario Velasquez from the house. It's going to be talking about shared characters for twisted equivariant K-theory for complex deep group functions.
Thanks for the invitation, for the opportunity, talking my home. This is the work with Thomas Schick in Göttingen. It's a new decomposition theorem in twisted equivariant K-theory. Okay, let me. Okay. Give an overview about this talk. We will start with the classical Chern character for vector bundles by Chern classes, and taking values in rational cohomology. Then how to define an equivariant character in finite groups, and then how to extend from the case of finite groups to compact groups. Then the rational decomposition theorem and some examples of this group is U2. Then how to extend this decomposition to twisted K-theory using covering spaces. And finally, the twisted equivalential character that we have constructed, the mean theorem and some applications to inertia spaces. Okay. So, what is a vector bundle? A vector bundle on a topological space, you can think X like a manifold, for example. A vector bundle on X is a continuously varying family of vector spaces, which is locally a problem. In some senses, we are assigning to each element in the topological space a vector space, but continuously, in a continuous way. An example of this is the tangent bundle. You take the sphere, and over each point of the sphere, you assign the tangent space. And if you put all these tangent spaces in one space, in one total space, it is the tangent bundle. Tangent bundle is the space that contains for each point the tangent space of this bundle. Okay. What is K-theory? K-theory is complex K-theory is the Grothendieck group of the monoid of isomorphism classes of complex vector bundles on space. Okay, this is the K0 group. This group is very important, but it's difficult to compute. It's very difficult to compute K-theory. Then the chain character convert this geometric information, this group, in cohomology. The advantage is that cohomology can be computed in a combinatorial way. You can use Mayer-Witten sequence or a cellular decomposition of the space to compute cohomology. Okay?
Sorry. What is the Grothendieck group of this?
The isomorphism monoid of isomorphism, the isomorphism classes of vector bundles is a monoid because you can take direct sum, like vector spaces, you can take direct sum, but the problem is that you don't have a inverse, additive inverse. Then when you add formally additive inverse, this is the Grothendieck group. Okay. The elements of K-theory correspond to formal differences between isomorphism classes of vector bundles. It's like when you have the natural numbers, it's like assigning the integers. Okay. Okay. So now consider, for example, a line bundle. It means a vector bundle when the vector spaces that we are attaching are all of dimension 1. It's a line bundle. And then we have that this is locally a product. Then consider a covering of the space when in each of these elements the bundle is trivial. It means that for every alpha there is an isomorphism between the vector bundle restricted to the open set to a product. What happened? We can take a point in the intersection of two of these open sets, and then we can trivialize with alpha, with P alpha, and we can also trivialize with P beta. Then we get two maps from the restriction of the bundle to these two products. And there is a way to translate the one trivialization in the other by this map, P alpha minus 1 composed with P beta. This map is the identity in the first component, and in the second component is a linear map. It's a linear map depending on the point. Okay. This map then is a map from the intersections to the invertible 1-by-1 matrices. These maps are the transitions functions of the bundle. Okay. We have the transitions functions of the bundle. We can reconstruct completely up to isomorphism the bundle. Okay. Okay. The transition map satisfies the co-cycle conditions. It means that we multiply GKA times GJK times GIJ, we get the identity on triplet intersections. Then, under central condition of the covering, that I don't want to talk about this, but if we have good coverings, this family of transition functions defines an element in the cohomology, in the first cohomology group of the space with coefficients in the C star, and by the long effect sequencing coefficients, it is isomorphic to the second cohomology group of the space with interior coefficients. This number, this cohomology class is the first Chern class. It's called the first Chern class. Okay. Now, if we have a general vector bundle, complex vector bundle, for example, of rank R, we can suppose that this, by the splitting principle, we can change the space, the base space, but I don't want to talk about these details, but suppose that these vector bundles can be decomposed as a direct sum of line bundles, and compute the first term class of each components. Let's say xi. Then the Chern character of the bundle E is the sum of the exponential of these Chern classes. What is the exponential? Just the exponential. But in this case, this sum is finite if we suppose that X is a finite dimensional space. For example, a manifold. If X is a manifold, then this sum is finite. It's the exponential of the Chern classes. Then the Chern character is a sum of exponential of Chern classes. Okay, this is the Chern character. And the main property of the Chern character is that it defines a ring homomorphism. It means that the Chern character of a direct sum of vector bundles is the sum in the cohomology groups. And the Chern character of a tensor product is the multiplication of the Chern character. And then it extends to K-theory, to vector bundles, or this formal difference of isomorphism classes of bundles. And then it defines a map from the K-theory, zero K-theory of X, to the cohomology, the even cohomology. It means the H0 plus H2 plus H4 and so on. It is important to know that this exponential needs to divide by this term n factorial. Then the cohomology has to take, we need to take coefficients in the rational numbers, not in the integers, because we need to divide by this. Okay. The theorem is that we have this map. If we tensor with the rational numbers, we have a ring isomorphism. In the K theory, tensor with the rational numbers, and the cohomology with coefficients in the rational numbers. Okay. Questions so far? Okay. Okay.
Yeah,
Okay. 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 Why the chain character is important or is useful? Because compute K-theory of spaces could be very big. For example, the computation of the K-theory of the sphere, the two-dimensional sphere, is a non-trivial result. It's the spot periodicity. On the other hand, the computation of the cohomology of the sphere is just a direct application of the major vector sequence. I don't know, the first exercise in a algebraic topology course. Then we can compute easily cohomology. We know the space, but compute K-theory could be very difficult. It's the bridge behind the Hirsebruch-Riemann-Roch and its formula, the first formulation of the index theorems, the Singer index theorem, in both chain character. And we can separate rational information from torsion. For example, one strategy to compute K-theory is first compute the cohomology. It gives the rank of the group. And then we can try to compute the torsion using other methods. Okay. What is the limitation? The limitation is that with cohomology, we only know torsion. Torsion-free part. To compute the torsion, we need to use other tools. Okay. So now suppose that we have a topological space like a manifold, smooth manifold, but with an action of a Lie group. For example, an action of the rotation group or an action of a finite group. We can play the same game. What is a vector bundle? But in this context. In this context, we will consider vector bundle with G action. What means that? A G vector bundle E over X is a vector bundle with G action in such a way that the action leaves the action on X. It means that here we have the space X and pull that. Here we have the vector bundle, map. We have a G action on X, we have a G action on the space E, in such a way that if we have a point in the space, and the action of an element maps X to GX, then on fibers, the fiber over X maps to the fiber over GX, but by a linear map. The action of G, the element G, is given by a linear map. It is a G vector bundle. Okay. What is equivariant K-theory? Then again, we can consider the set of isomorphism classes of G vector bundles with the direct sum operation. This is a monoid. Then we add inverse formally, the Grothendieck group, and then it is the K-theory group. It is the zero K-theory. What happens if we try to use chain character to compute this group? The problem is that the chain character doesn't see the symmetries given by the action. For example, suppose that we have suppose that that our space is a point with the trivial action, obviously. What is a vector bundle? A G vector bundle over a point. First question: what is a vector bundle without action over a point? Suppose that our space is just a point. What is a vector bundle over this point? Just a vector space. Okay. And what is up now? This is a vector bundle over a point. This is just a complex vector space. And now suppose that we have the trivial action of G. What happened here? How G acts on B. By this condition, by the condition of the linearity of the action on the fibers, it says that a vector bundle over a point is just a vector space with a linear action of G. It is a representation of the group. Then the K-theory of the equivalent K-theory of a point, it is just this ring. It is the representation ring. What is the representation ring? It's the same thing, but here we put G representation. Okay, and it depends on the group. If the group is big, this ring could be very big. But if we compute the detection character, it is only see the topology of the point, and then the cohomology is just of rank 1. Then we need to implement the action on the cohomology side. Okay. Then if we want to define an equivariant character, we need to add or consider the action on the fibers, full representation of the isotropy groups, and also the topology of the fixed point spaces. Okay. So, be a complex group, let X be a finite GCL complex. What is the goal? The goal is to construct a computable chain character for equivalent K-theory that remembers the isotropy groups, like in this case, the representations of the isotropy groups, and also the topology of the fixed points. The construction has 2 steps. The first one is that K-theory or the torsion-free part of the K-theory using maximal topological cyclic subgroups. I will define what is this. And the idea is to reduce to topological cyclic subgroups and then reduce again to apply a Locke-Chern character, non-equivariant Locke-Chern character, and impose some compatibility conditions. Okay, that I will explain in some minutes. First start with the case of finite groups. The G be a finite group acting on a space. For 2 elements in the group, we can take the G fixed points under the action. Then we take a point that is fixed by G and apply the action of H. It gives a fixed point by this H, G, H inverse. And we can take the pullback of these actions over the K-theory groups. We can put together all the K-theory groups of the fixed points. The pullback of this map defines an action of the group on this diagram. Okay. And there is a theorem of Atiyah and Segal, 1989, I don't remember exactly at this moment, but the theorem says that if we want to compute the equivalent K-theory of the space with complex coefficients, it is isomorphic to the fixed points under the G action, the action induced by these pullback maps, the G invariant part of this diagram. Okay. How to prove this result? The idea is that we suppose that X is a GCW complex. It means that the space is constructed inductively, starting with points, or starting with orbits, and then attaching a disk using certain maps. And this condition allows us to use induction. Then the idea is to prove the isomorphism when X is an orbit, and then use induction to extend this isomorphism to every GCW complex. That is the idea of the proof. But the important thing now is, important thing is that we have reduced the computation of the top of the equivariant K theory to a computation of K theory, but without group, ordinary K theory. Then here we have a group or a K theory group when we can apply the ordinary or the classical chunk character. Because here we don't have group, we can apply the chunk character in the beginning. Okay. Then we have this theorem. We apply first the Atiyah-Segal theorem to obtain K theory of the fixed points, and then chunk character to obtain cohomology with complex coefficients. Then it means that we want to compute the torsion-free part of equivariant K theory for action of the finite groups. We need just to compute the cohomology of the fixed points and understand the G action of the G action on this vector space. That is the localized chunk character. But if we want to, sorry. Okay. The problem is that if we want to extend this to Lie groups, we have a lot of problems. For example, this sum is not finite in the case of Lie groups. Then this is an infinite dimensional vector space, and then we have to consider the G action. We know how to do that and compute. And then maybe this something like that is true, but it's not computable because the space is infinite dimensional. Then we need to find an alternative. Okay.
What about the product structure with the right side of the equation?
Again, we have a ring structure.
Oh,
yeah.
The right side.
In this case, it's complicated. It's complicated. Yeah, here we have the product induced by the tensor product. We can try to define a product in this side to have a ring isomorphism, but it's difficult. We need to use induction and it could be complicated. I think that is possible, but I'm not sure in this moment, but it could be complicated. Okay. So we want to extend this kind of decomposition for a compact Lie group action. And what is the idea? The idea is that these results for finite groups suggest that the rational information should be detected by cyclic type subgroups. And the analog for compact Lie groups of cyclic groups, subgroups is the notion of topological cyclic subgroups. What is a topological cyclic subgroup? Is the closure of a cyclic group. Or in other words, is a product of a torus with a finite cyclic group. And what is the idea? The idea is again a finite decomposition that is true in the one point case. Then try to extend this to orbits and then apply induction on cells to extend the results to finite GCW complex. We can think this GCW complex like, for example, manifolds, smooth manifolds with a smooth action of the Lie group. Okay. 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 Sorry. The definition. What is a topological cyclic subgroup? Is a subgroup of the Lie group that is isomorphic to a torus times a finite cyclic group. It is the same as the closure of a cyclic subgroup. Okay. Some properties. Every element of the group is contained in a topological cyclic subgroup. A compact Lie group has finally many conjugacy classes of maximal such subgroups. And for example, if G is connected, there are precisely one conjugacy classes of topological cyclic subgroup, and it corresponds to the conjugacy classes of the maximal toric. Okay. the first part of our decomposition is the following. You can consider the representation ring, but with rational coefficients, tensor with Q. It is isomorphic to this inverse limit. The inverse limit is taken over the family or over the set of conjugacy classes of maximal topological cyclic subgroups. Under the relation given by subconjugation. I will explain this in more detail in some minutes, but the idea is that we can recover all the rational information of the representation ring using just topological cyclic subgroups. Okay. What happened with connected groups? I previously said that when disconnected, topological cyclic subgroups corresponds, maximal topological cyclic subgroups corresponds to maximal tori. Then this family, in the case of disconnected, is just one. It's just the conjugacy classes of the maximal tori. Then this inverse limit, in the case of disconnected, is just take the representation ring of the torus invariant by the Weil group. It's a classical result of connected groups. Representation ring can be computed using the representation of the maximal tori invariant by the Weil group.
Which one is harder to compute? The right side or the left side?
Also, the right side is easier to compute because this group is abelian, and this is a polynomial ring, a Laurent polynomial ring, and then the difficult part is to understand the action of the Weil group. Yeah, but this side is easier. Okay. Okay, so what happened in general? Suppose that we have a space X with an action of a compactly group, and consider an element and take the isotropy group of this element. The orbit type of this element is the conjugacy class of this isotropy group. Consider a fixed isotropy group L. Then we define this set MTC. The set of conjugacy classes of maximal topological cyclic subgroups, but inside of L. Conjugacy classes in G, but of maximal topological cyclic subgroup of inside the isotropy group. Okay, we are taking the isotropy group on each level, taking the maximal topological cyclic subgroups, and this other set OTC is the conjugacy classes of maximal topological cyclic subgroups for some orbit type. Then we take the isotropy group, take the maximal topological cyclic subgroups, and put all this in only one set. This is the OTC. A result, if X is a finite GCW complex, then this OTC is finite. This is a consequence because this kind of spaces has only finite orbit types. Well-known result. Then this set is finite. Okay. Now, consider this direct sum. As this set is finite, then this is a finite dimensional vector space. And then we have a map from this equivalent K-theory group to this direct sum given by restriction. And take a G vector bundle over X and restrict to the pixel points and restrict the action to these subgroups Q. But the thing is that this map, the canonical map, is not surjective. It's not surjective. The image of this map is not complete vector space. The image is characterized by some compatibility condition. The subgroup, that is the image of this restriction map, is denoted by CSCG of X and is defined as follows. Okay. Suppose that we have two topological cyclic subgroups, maximal topological cyclic subgroups, that such that Q prime is subconjugated to Q. It means that we have this thing. Then there is an inclusion of fixed point space. Reverse this inclusion. We have an inclusion in the other way. And then we say that a tuple of elements in this group, in this group or in this vector space is compatible. Is compatible if you take the Q prime component, take conjugation by this G, and then pull back. This map applied to XQ belongs to this KTL group. Q prime, then conjugation, then the action is the group that acts is this one, and then pull back the space, pull back along this inclusion, and the space is XQ. And we can also take the Q component and take restriction of the group using this part. And then we impose the condition that both things are equal. Both these two maps are equally evaluated in XQ prime and XQ. This is the compatibility condition. And the result is following. Oh, okay. Blah, blah, blah. The result is the following result. This is our first theorem. The G be a compatible group and X a finite GCW complex. Restriction to fixed point space induce an isomorphism. Hence, we can consider this group embedded inside this direct sum. It's not subjective. The image is characterized by these compatibility conditions. Okay. Allows us to compute this equivalent K-theory group with rational coefficient using just cyclic subgroups and fixed. An important thing is that the action of the group Q over the fixed points is trivial. Then we are reducing the problem to compute that abstract K-theory group to compute an K-theory group of an equivalent K-theory group of an action of a cyclic group, but a trivial action. Okay. How to prove this theorem? The case when X is a point, we already have the result because this inverse limit theorem for representation rings. When we have an orbit, we have an induction principle for equivalent K-theory. Then we can pass from this G equivalent K-theory to the L equivalent K-theory for a point. And then it is the case of a point, then we can use the first step. And then we need to compute the fixed points of the Q fixed points of an orbit and compute. And finally, we can use induction. As the space X is constructed using attaching maps, attaching disk along attaching maps, then we can use Mayer Vietoris and induction to extend the result to every GCW complex. Okay. Then, how to, using this decomposition, define an equivariant character? Since on each term of the direct sum, Q acts trivially on the fixed point space, then there is a canonical identification between the Q equivalent K-theory the Q equivalent K-theory of XQ with the representation ring of the group Q tensor with the K theory of the fixed point, but note that here we don't have group. It is a non-equivalent K theory group. Then we can apply the Chern character, the classical Chern character in this part. Then the equivalent Chern character is just the following composition. Start with the geoequivalent K theory, then take the restriction map, and in this, on each summand, use this decomposition, get this tensor product, and then in this part apply the identity, okay, and in the second part apply the Chern character. Then we have a way to compute or to express the geoequivalent K theory with rational coefficients in terms of cohomology, non-equivalent, just cohomology of the fixed points tensor with these representation rings. And then we can define also the compatibility subgroup condition at the level of cohomology. And then we have this theorem, the G be a compact Lie group, and X finite GCW complex. Then there is a functorial map from the geoequivalent K theory to this direct sum, such that after tensoring the source with Q, this map is injected, and the image is exactly this compatibility subgroup, geoequivalent X. This is our first result in geoequivalent K theory. Example, suppose that our space is the group SU2, the rotation group, with the conjugation action. Means SU2 acting itself by conjugation. Every element is conjugated to an element of this kind. And the isotopic group of each element is decentralized because the action by conjugation. Then we have two cases. If the angle is 0 or P, the element is central. So if centralizer is everything, yes, you do. If the angle is between 0 and P, its centralizer is the maximal torus, the corresponding maximal torus, then the maximal torus of rank 1. But both isotopic groups, this one or this one, have up to conjugacy the same maximal topological cyclic subgroups. In this case, the maximal torus. The maximal torus inside S1 is the maximal topological cyclic group subgroup. In this isotopic group, SU2, the maximal topological cyclic group subgroup is again the same group. Therefore, this set OTC is the maximal torus, the conjugacy class of the maximal torus. Then, for this case, the fixed points are the centralizers that corresponds to the torus, and the bile group is the Z2. Then, the compatibility subgroup conditions corresponds just to take the invariance by the bile group. Okay. Then the K theory, the equivalent K theory of SU2 equivalent K theory of SU2 with the conjugation action is isomorphic to this invariant group. The representation ring of the maximal torus tensor with the cohomology of the torus, but as a space, as a topological space. Here as a group, but here as a topological space, invariant by the bile group. The bile group acts by inversion on T, then on the representation ring, the action is just set by inverse, and in the cohomology mapping W or omega to minus omega, We can compute the invariants, blah, 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 blah. But the result is that the K-theory has rank 2 on 0 and 1. Okay. Question so far? No? Okay. Now, how much time do I have? 8 minutes? 8 minutes, okay. Great. Now, we can also consider a more general version of equivariant K-theory. It is the twisted K-theory. Let us start with twisted vector bonds. What is a twisted vector bond? Remember that when we have a line bundle, there is a set of transition maps that satisfy the co-cycle condition. What is a twisted vector bond? A twisted vector bundle can be defined as a family of transition functions, like a transition function, but satisfying not the co-cycle condition. Instead of that, the twisted co-cycle condition. This condition, Gij, Gjk is equal not to Gik. Instead of that, Gik, but multiplied by a twisting term. This twisting term is a check co-cycle coefficient in the circle. When alpha is 1, this is just the usual co-cycle condition. And what is twisted K-theory? Twisted K-theory is the Grothendieck group of this, the monoid of isomorphism classes of these objects, alpha twisted vector bonds. Alpha is fixed, alpha is called the twisting, and the elements in these twisted K-theory groups are formal difference between isomorphism classes of these kind of objects. It's twisted vector bonds. Okay. And we have also a twisted Chern character for this kind of objects. How to define this? The twisting alpha, we can assign, we can assign to the twisting alpha three differential form. Then represent this twisting by a closed tree form, H. Choose local two forms in such way that the derivative of bi is equal to H, restricted to a certain covering. Locally, a twisted vector bundle is just an ordinary bundle. Then, for this ordinary vector bundle, we can compute the Chern character, as before. The problem is that when we try to glue all these local forms, it doesn't work. Because the transition functions have this twisting, then we need to multiply by a factor, an exponential here, that correct this error. Then we can glue these local forms in an inhomogeneous differential form. And the problem is that this omega is not closed in the usual differential, stereo differential of differential forms. Instead of that, it is closed, but with this modified differential, this twisted differential. It's the usual differential of the RAM cohomology, but with this term given by multiplying by H. In this modified differential, we have that the differential of omega is 0. Okay, this factor repair the error. Then the theorem of Matilla and Sigal is that we can compute the cohomology, but the rank cohomology, but not respect the usual differential. Instead of that, with this twisted differential, then it's a twisted the rank cohomology. And we can define a twisted term character that becomes an isomorphism when we tensor with the complex numbers. So, okay, there is also, sorry. Okay. Okay. We can also define twisted G equivariant twisted key theory in a similar way like in the untwisted world. And equivariant twisted K theory also has a certain Grothendieck group. And we have also a theorem with relating the twisted equivariant K theory with rational coefficients with compatibility subgroup inside a direct sum of twisted equivalent K theory with respect to cyclic subgroups with trivial action again. And then the idea is if we want to define a term character, we need to express this twisted equivalent K theory group with respect to cyclic subgroups in terms of non-equivalent twisted K theory groups. To do that, we need to consider the monodromy of the twisting encoded by a covering space. How much? 2 minutes? Okay. So the idea is that when we have a twisting over a trivial space, over a space with trivial action, it can be determined by 2 data. The first one is a non-equivalent twisting and a principal bundle. And with this description, we can convert a equivariant K theory with trivial action into a twisted equivalent, into a non-equivariant twisted K theory group, but with compact support. C denotes the compact support. And our result, our result is following. We have a version of the term character, of the twisted term character. Show you the our final result. Okay, yeah, that is our final result. Consider a compactly group, X a finite GCW complex. Continue this like a manifold with a smooth reaction. Here, G equivalent twisting. Then there is a functorial map from the G equivalent twisted K theory to this finite direct sum of what is this? This is a twisted cohomology respect to some tree form with compact support of some covering space over the fixed point xq. This zq is a covering space over the fixed point space xq. And it's such way that when we tensor with C, this map is injective, and each image is exactly a compatibility subgroup depending on X, the group G, and the twisting P. Okay. And final applications. So final application, we have this result that prove a conjecture of Adem, Cantarero, and Gomez. Let's say that we can compute the twisted K theory for certain inertial space in terms of the cohomology of the fixed points tensor with some group algebra, rational group algebra, invariant by the by. Okay, so thank you.
Maybe we have time for one quick question. Seems like everybody wants to go to lunch. Okay. So that's it for the morning, and we resume at 2:30. Thanks, Mario.